All right. I wanted to point out the formula sheet that Frank has, and if you were able to go to his workshops, and that's great. If not, you can still get access to his stuff. If you go to Cañada College's homepage and go to Student Services, or maybe you can just search the Learning Center or something. You click on the Learning Center site, and there's a math lab, or maybe you can just look for math lab at the Cañada search. You hit the math lab, and you go down in the bottom. His poster that's on the side of the wall there, it's pretty much the same thing as this. His schedule is here. And then down here it says see and print a Math 200 outline. So if you click on that, you'll see a PDF of his summary. It's like it's 13 pages. It's a lot of pages. And if you go to his workshop, you'll get one of these copies. I just want to focus on, he does it by chapters, and so his chapter 5, discrete probability distributions and using the calculator. Down here in this block, that has all the summary for the binom PDF and CDF business that you'll ever need for this class. So when you see the words, the phrases at most or at least, less than or greater than, then these are the symbols that you would use, and these are the commands that you would use to finish that off. So I think if you're able to just follow through some of these things, and when you look through the review sheet and look at the solutions for the review sheet, and then maybe even look at the video solutions for the review sheet, there's one set of problems that deal with the binomial distribution, and then it shows the calculator commands for these things. So if you want the exact value, that's PDF, and if you want anything else aside from the exact value, then you're going to use a CDF, and sometimes you're going to take the CDF itself, or sometimes you'll take the CDF and subtract it from 1. And these are the 4 different scenarios where that would come up. All right. We don't have too much time to talk about this, but hopefully this sheet will be enough to get you going. I'll put this in our notes as well, but I suggest that you go through the Cañada College website and look for the math lab, and then look for this to download. So let's go to the last section in chapter 5, which is finding the mean and the variance and the standard deviation for a binomial distribution. So this is 5.4. A binomial distribution is a discrete probability distribution. So don't write these formulas down, because you either wrote them already or decided not to write them down, because they're exact same formulas as we saw from before. The idea is that you can use these formulas for the binomial distribution if you construct a table like we did in our calculator. If you construct a table, then you can do this, x times p of x, and then add them all up. The difference is, from what we did earlier, we did it with only 2 random variables. For the binomial distribution, you have, example that we had, from 0 through 5, there's 6 random variables there. And then sometimes you go as much as 40 or 50 or 100. So you definitely want to stay away from these formulas. This is for a discrete probability distribution, and a binomial distribution would work too. But if you have a binomial distribution, we have another set of formulas to use, and these are a lot simpler. If you have a binomial distribution, one of the first things you'll do is you need to identify the n and the p. because the binomial distribution has a fixed number of trials, that's n. It has a constant probability, that's p. Once you know the n and the p, you'll eventually figure out q. And then once you know n and p and q, then you can find the mean, variance, and standard deviation just by multiplying them. Well, the standard deviation, you multiply them and you take the square root. So still, these are all easy formulas. And it's so easy that we can quickly go back to our example with the slot machines 5 times. And we can ask, on the average, what is our number of expected wins if we play the slot machine 5 times? I can tell you now, the number of expected wins is probably 0, right? So we'll probably won't get exactly 0, but we should get something close to 0. So in that case, the mu will be 5 times 1 over 2,000. Which in our calculator should be easy to do. I guess I could do this without a calculator. Nah, why don't you just, what's 5 divided by 2,000? So a really small number. So you're expected to win about 0 times. The variance is the standard deviation squared. 5 times 1 over 2,000 times the complement q, which is 199 over, or 1999. Did I put too many 9s? What? That's right. Over 2,000. So whatever this turns out to be, what is it? 0.0024, and then to find the standard deviation, I'll just take the square root of that, or Madison will take the square root of that. 0.05. So still numbers that are really small, less than 1 for binomial distributions. For this particular binomial distribution, we're expecting really small numbers because, you know, when we play slot machine, we just play it 5 times, we shouldn't be expected to win. So that's a simple example. I have some more interesting examples for this scenario or this type of problem that I got from the book, and let's take a look at those. Oh, you should know this already, but just in case, q is equal to 1 minus p, right? It's one of those things that's going to keep coming up again and again. So p and q are complements of each other. Just think about it that way. All right. Interpretations, usually I just fly over this page. It's the range rule of thumb again. 2 standard deviations away from the mean as our usual values. All right, here's an example. This is interesting, and this is that gender selection business that I was talking about. And I picked 2 of them to kind of contrast, compare and contrast the 2 different scenarios that you might have. Sorry, give me a few seconds here. So this is our problem. In a test of X sort method of gender selection, 574 babies are born to couples trying to have a baby girl. And out of 574 babies, 525 of those are girls, based on this place that they went to. If a gender selection method has no effect and boys and girls are equally likely, find the mean and standard deviation for the number of girls being born in the group of 574 babies. So imagine this as a binomial distribution scenario. So this is a binomial distribution, and we'll show that this is a binomial distribution by taking a look at the fixed number of trials. We have a fixed number of trials, right? What is our fixed number of trials? 574. So we have 574 babies that are being born. Now, for each of these couples, we'll assume that the trials are independent, that the baby being born from one couple has nothing to do with the baby being born from another couple. That makes sense. Out of the babies being born, it just disappeared, huh? Independent. Out of the babies being born, they can either be a boy or a girl. In this case, our success is a girl. And our failure is a boy. Again, that's just relative to the problem. It has nothing to do with a success or a fail. And the probability for success, and provided we assume that some method here has no effect on the boy-girl ratio, probability of getting a girl and a boy is just at 1/2, right? So our P is 1/2, that's the probability of getting a girl, and if needed, our Q is also equal to 1/2. But for the sake of identifying a binomial distribution, the N and the P are the important numbers that we need to get out of this, and so this is a binomial distribution. Now let's find the mean and the standard deviation for this scenario. Our mean, according to the formula, is going to be, so remember, if you were to do a table and use the first set of formulas, that's 574. That's a long list to deal with. So we'll use a shortcut, and remember that the mean is N times P. So 574 times 1/2. So what's 574 divided by 2? 200 what? 87. So out of these babies that are being born, we should expect 287 of these babies to be girls and 287 to be boys. Just split down the middle. So that's our expected value. What is our standard deviation? So remember, the standard deviation is the one with a square root. It's like finding the variance and taking the square root. So we need the variance, which is N times P times Q, and then we need to take the square root of that. So this is a square root of N times P times Q, so that's 574 times 1/2 times 1/2, or 574 divided by 4, I guess. Okay, however it is we deal with this, what is our answer? 12? Round off to, let's round off to 1 decimal place. 12.0? 11.9 something? Okay. All right, so our standard deviation is 12. So, questions? Oh, we need to take the square root still? Okay, take the square root. What is it? Right, should I do it? I'll do it. So I got 574 times 1/2. I'll just put 0.5 here so I don't have to mess with fractions. Times 0.5. And then I want the square root of that. That looks right. Square root. So second function and this thing, square root of the answer. Yeah, so 12.0. Is my standard deviation. So based on my mean and standard deviation, if I have a range of values, 287, and then my range of usual values, if I add 2 times 12, so this is 287 plus 2 times the standard deviation. This is mu plus 2 sigma. So add 24 to this, 303. Did I add that right? Probably didn't. 287 plus 24, yeah. 311. 303, what? And then 287 minus 24. 263. So what they're saying here is that the usual range of values span between 263 to 311. So if we had 574 babies born, it would still be usual out of those 574 babies, it would still be kind of usual to have 311 girls on the high end of it. Or it could be usual, it would still be usual if we had 363 girls on the lower end of the spectrum. So these are your usual values. Now, when these 574 couples that had babies went through this X-sort company, and they got special packages and special diets and special exercises that they had to do to try to make this baby a girl. You know, they had 574 clients, and it turned out that 525 of them actually had girls. 525, based on our analysis here, is that a usual or unusual value? That is very unusual. That's unusual. That means there must have been something going on, and that means that their packages must have been really effective. Because, whoa, 525 babies were girls out of this 574 people that had kids. So they must be doing something right. Right? So if they went through the test and it turned out that 311 of them were girls, okay, well that still could be usual. That still might happen, probability-wise. So maybe there's nothing interesting in their elixirs, in their mixes, in their diets, in their special pills. So because 311 would have been a usual value. It seems pretty high compared to 574, but it still would have fallen under our usual values. But 525 out of 574, that is very unusual. Okay? That sound good? All right. You guys should research that company if it actually exists. It's an interesting premise by the author, but I don't know if it really exists or not. Okay, so that's an example. And then I had another example here where It's 125, but it's the same sort of thing. So I'll leave this here, and then you try at home. This is from the homework set, also from section, whatever section we're on, 5-4. In the back of the section, there's those exercises. So, all right, that is it for Chapter 5. So our main focus in Chapter 5 was discrete probability distributions. I can tell you now that in the test, you probably, if not on this test, then maybe in the final, that I do like the simple probability distributions where there's two scenarios. In this case, the insurance company, you live or you die. Or in the practice test, I had one where you win or you lose. There's two scenarios, and then you figure out your probability distribution table, and then you figure out your expected value. I also have a whole page on binomial distribution, where you have to use binom PDF or binom CDF or any of those combinations. So you have homework problems in that, you have a quiz problem in that, and you have the review. There's a problem in the review that has that. Okay, we're off to Chapter 6 now. So I started to record Chapter 6, and I realized that as I was recording Chapter 6 in the PowerPoint that they have from Chapter 6, that they really focused a lot on Table A2, using the table to figure out the probabilities and the problems. And so I recorded it, and then I just had to stop and say, I really don't want to focus on using the tables. And so what I did is I chopped up the PowerPoint presentation, and so this is going to be considerably different from the PowerPoint presentation that they have. I'm using the same slides. I added things and I took away things. And so I'll make sure to post this up in the notes. And if you got used to downloading their PowerPoint presentation, you should make sure that you download this one as well so that you can see the difference. This section has one or two extra sections that we will not cover in the class and I will not test you on. The main thing that I crossed out here, used to be here, was using the normal distribution to approximate the binomial distribution. Now, since we have technology to figure out how to compute things in the binomial distribution, I really didn't need, I didn't think that there was a need to do this approximation business, so that was crossed out. So in this case, we're really going to be focusing on 4 sections. First section I don't count because it's just an overview. So really the standard normal distribution and the normal distribution, and then the sampling distributions and the central limit theorem. And hopefully we can finish that in 45 minutes. So, overview. Our main focus for this chapter is the normal distribution. Now, the normal distribution is an example of a continuous random variable or a continuous probability distribution. There is going to be one other continuous probability distribution that we will cover called the uniform distribution, and we'll just breeze through that kind of quickly. But when we get to the normal distribution, because this is a continuous random variable, we're not going to be looking at a table of values like like in the binomial distribution we had x and p of x. We won't have anything like that because it's continuous. There's an infinite number of values that we're talking about. So the best way to do that is with a graph. Just like the binomial distribution, which had a complicated formula, this particular normal distribution also has a complicated formula. And the formula looks like this. And again, fortunately, this is the only time we'll ever have to see this. Unless you become a math major at some point, in which case this will become an important part of your life. This is not something that we'll ever need to see again. So when we talk about normal distributions, the graph of the normal distribution is important. So the bell-shaped curve is what we want to remember. Oh, one more thing about the bell-shaped curve is that the mean is always going to be in the middle. Okay, regardless of this bell shape is going to shift around, it's going to get steeper and shallower or whatever. The mean is always going to be in the middle. Okay, let's. The uniform distribution is technically covered in 6.2, but I'm going to call it 6.15 because 6.2, the title for 6.2 is standard normal distribution. So this is where I changed the slides slightly, and it's not a big deal. So I want to cover normal distribution, or uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over a range of probabilities. The graph of the uniform distribution, because when we're talking about continuous distribution, we're focused on the graphs. The graph of the uniform distribution will result in a horizontal line, and so if you count the area underneath, we're looking at a rectangular shape. So Michael asked earlier about what types of distributions or what types of random variables are continuous versus discrete. And I said discrete are things that usually you would count. And then continuous, he mentioned a whole bunch of them, like heights and weights and times. So one of the more popular examples for a uniform distribution is time. And so they give an example here of a uniform distribution of time, but they didn't tell you what the problem was. They just show you the graph. So when we get to that slide, we'll talk about the scenario where you might have that particular graph. Okay, the density curve is the way we're going to describe our continuous probability distribution. And density curve, if you could try to remember back where we're talking about the properties for a discrete distribution, the discrete distribution, let's do this in a different color. Our discrete random variables. We have the sum of all the probabilities add up to 1. Well, saying the total area under the curve must equal to 1 is pretty much the same thing as saying the sum of all those probabilities are equal to 1. Except because it's continuous, we can't think about adding up those probabilities because there's an infinite number of them. So instead of adding up those probabilities, we refer to the graphical representation of it. That's the density curve. And the area under the curve has to equal to 1. So that bell-shaped curve, the area under the bell-shaped curve is equal to 1. And then every point on the curve must have a vertical height that's 0 or greater. And that's the same thing as saying that your probabilities for each of these probabilities is between 0 and 1. It's greater than 0. They don't say here that it's less than 1, but it's got to be less than 1 because the area under the curve has to be less than 1. One more thing to point out, just as an interesting fact, it's not a big deal. Is that the bell-shaped curve and that weird formula that we saw that I told you never have to remember, that particular formula, if you were to graph that formula, technically that graph will never touch the x-axis. That graph technically goes on forever to the left and to the right without touching the x-axis. So the area under the curve has to equal to 1. the area under this curve, although it never touches the x-axis, the area is still going to equal to 1. That should blow your mind if you're really thinking about it really hard. But if it's not blowing your mind, don't worry about it. Yeah, it can be 0, but in this particular case, another density curve, another example of a density curve is something like this, where it's 0 everywhere else, and then it pops up over here, and then it has an exponential decrease. So it's 0 in all these places over here, and then it bumps up to something that's not 0. So in this case, this will never be 0, so it has a height that's 0 or greater, and that just means this will never have a height of exactly 0. It'll have a height that's really small, but it'll never be 0. So yeah, the normal distribution will never touch the x-axis. Will never have a height of 0. You would think, but no. Mathematically, it goes on forever without touching the x-axis. Practically speaking, when we're talking about a normal distribution, say this is the average height of men, what did we say? It was like 70 inches or something? We just made that up. Average height of men is 70. Now, technically, you would want to trump this at 0, right? You can't have anything that's has a height that's less than 0. That doesn't make sense. Even a height of 0 doesn't make much sense. But mathematically speaking, we still consider this to go off to infinity. And we consider the maximum height also to go off to infinity. Now, it doesn't make sense to have somebody that's, 3,000 inches tall, but mathematically we still need to consider that. It will have a very small probability, but we still need to consider that. Okay, so that's a density curve, and more specifically for our normal distribution, our density curve goes to positive and negative infinity in both ways. Okay, let's talk about this idea of a probability. We're interested in finding probabilities of things. And since we're talking about a density curve having an area of 1, that's equivalent for us, that will be equivalent to finding probabilities. So for us, the area is the same thing as a probability. When we're asked to find a probability, what we're doing mathematically is we're really finding an area. And geometrically, this would be easy for us if the area was a rectangular region. So if we had a uniform distribution, then we're looking at finding rectangles, and you need to find the area of a rectangle, base times height. But when we start talking about the normal distribution, well, finding the area of that is not geometrically possible for us. So we'll have to rely on a table. Nope, we're going to rely on our calculators. They do talk about the table here, and I'll minimize the discussion of tables for us. So here's their example of a uniform distribution, and they didn't give the scenario here, but let's say there's a class that lasts for, there's a 50-minute class. 50-minute. So I'll try to create a scenario around this example. Class is 50 minutes long. But we can say, but class usually ends between 50 minutes to 52 minutes with an equal probability. So this would be the scenario for this particular graph. So the graph is a horizontal line, and then we trumpet from 0 or 50 to 52. And then we're saying that this class has an equal amount of chance of ending between 50 minutes to 52 minutes. So a question that they can ask you that would give you this answer would be, what is the probability that the class will end between 51.5 to 52 minutes? Question mark. What's the probability that the class will end between 51.5 and 52 minutes? So your answer is, this is 51.5 and this is 52 minutes, and you want to find the area under the curve between these two values. Since this is a rectangle, the area is going to be base. The base is the difference between 52 and 51.5 times the height. The height is just whatever that height is, which is 0.5. And so you just multiply that. And so this is what they got. So it looks like there's a 25% chance that your class will end between 51.5 and 52 minutes. So this is an example of a continuous random variable, and this is a continuous random variable represented with time. Okay? All right, so this is just to throw an example of a uniform distribution. You'll have a few uniform distribution questions on the homework. So whenever you see uniform distribution, keywords to look for in a uniform distribution is that equally likely or equal probabilities, and then that would mean it's uniform. Or they might actually flat out say uniform distribution, in which case you know it's going to be a rectangular region. Okay? All right, but our focus in this chapter is the normal distribution, so let's move on to the normal distribution. So we'll focus, in this section, we'll focus on the standard normal distribution. And the standard normal distribution is a special normal distribution that has some certain properties with the mean and standard deviation. And then in the general normal distribution, it'll be a little bit different. So in this section, we take a look at the standard normal distribution. It has these three properties. It's bell-shaped, the mean is 0, and the standard deviation is equal to 1. Now, for a regular distribution, regular normal distribution, normal distribution, it's still going to be bell-shaped, but the mean is not necessarily going to equal to 0, and the standard deviation is not necessarily going to equal to 1. So the difference between a standard normal distribution versus a regular normal distribution is that the standard normal distribution has a mean that's equal to 0 and a standard deviation that's equal to 1. But a regular normal distribution can have a mean of anything and a standard deviation of anything. A normal distribution can be a standard normal distribution. If your mean was 0 and standard deviation is 1, then your normal distribution is standard. And I kind of didn't want to make a big deal out of this because what I would like to do eventually is treat everything as a regular normal distribution because, like you said, a standard normal distribution is just a special case. The reason why they're making a big deal out of this is because in almost every statistics class, statistics book, statistics, those laminated sheets that you would find in bookstores about statistics study guides, all those have tables that's related to the standard normal distribution. And in the old days, before the use of a lot of technology, what people would do is they have a regular normal distribution, they would standardize it. And I'll show you the process of standardizing it to a standard normal distribution so that they can use those tables. But for us, we're just going to use the calculator and treat everything as if it was a regular normal distribution anyways, because we can find those same values now with technology without having to rely on that table. I mean, realistically, when you go out into the real world, are you going to be carrying a table with you or a calculator? No, you're not going to be carrying a calculator either. In a real world, are you going to have a table accessible to you or Excel? Well, you're going to have Excel accessible to you, and Excel has a way to find out these probabilities just by using a regular normal distribution. So, this isn't a very good definition of a standard normal distribution, but for our sake, let's just use what they have here. A standard normal distribution is a probability distribution with a mean that's equal to 0, a standard deviation that's equal to 1, and it has a bell shape. It doesn't say bell shaped here, so maybe I'll write it down. And the density curve is equal, the density curve is equal to 1. Let's squeeze in the bell-shaped density curve. So that's our distinctive property for a normal distribution, is that it's going to be a bell-shaped. Now, saying bell-shaped is kind of loose, and if you were to say this to a mathematician, they're going to complain and say bell-shaped. There's a lot of bell-shaped curves around. More specifically, it's based on that formula that we saw earlier that we don't ever have to memorize. So for us, just using the word bell-shaped will refer to a normal distribution. And the other important property is that your area is equal to 1, but that's true for any probability distribution anyways that we're going to consider. So it's all there. All right. How do we find probabilities for our bell-shaped curves? Well, they're going to focus on the table A2, which we won't, but I feel like I need to show you how it works anyway. So we'll talk about an example of finding this in table A2, and then we'll jump out and take a look at how to do it on a calculator. So other methods, Excel has a way to do it. For us, we'll focus on TI-83. If you ever need to find out a normal distribution probability using Excel, just YouTube it, and you'll find it there. And they'll tell you exactly what calculator or what command to type in Excel to find your probability. This is our table. And the difficult part about this is that sometimes a table goes through all the negative values, but if you pull out another table from the bookstore that has the cheat sheet for statistics, maybe their table might be a little bit different. It all comes with the same sort of values anyway, so it's not a big deal. So this table is assuming that you have your probability distribution, and then you're given a value that they're calling it a z-value. Now, we've heard z before, right? Remember where that was from? Z-score. It's exactly the same. This is normalizing so that the mean is 0 and standard deviation is 1. How many standard deviations away from the mean? We use a z-score to determine how many standard deviations away from the mean, and that's exactly the same numbers that we'll be using for the standard normal distribution. So in our standard normal distribution, what they're looking for here is the probability, the cumulative area to the left. So I don't know if you look at the table A2 in the book, if it actually has this drawing, it might have this drawing. But if it does, this is what they mean. If I go to negative 2.84, if I want to find this cumulative area to the left from minus infinity to negative 2.84, I would look at my table and look for negative 2.84. And this area here is 0.0023. And that area would correspond to some sort of probability if I was doing a probability problem. Okay, so that's how you would use a table. Okay. Instead of using the table, though, we're going to use a graphing calculator. So this is a problem that I have. This is a problem that's, I think it might be an example in the book, and I actually reprinted this. Here. So let's take a look at this problem and see if we can make sense out of it and be able to do it using our graphing calculator. Thermometers have an average reading of 0 degrees and a standard deviation of 1 degree for freezing. So this is a thermometer company that's building thermometers. And not all thermometers are perfect, right? So if you put it at the freezing point of water, your reading might be 0, but it might be a little bit off. It might be 0.5 or maybe 1.5 degrees. So this is asking if one thermometer is randomly selected, find the probability that at the freezing point of water, which is supposed to be 0, the reading is less than 1.58 degrees. Okay? So you could try to think about the scenario with the thermometers and everything, but if you want to try to just shift your thinking now into how would I do this problem in a test. So there's a couple of things to watch out for. First of all, you are given a mean and a standard deviation. And the mean is 0 and the standard deviation is 1. So this must be a standard normal distribution problem. So you're given a mean and a standard deviation. And they want you to find the probability that the reading is less than 1.58. So I'm going to draw a graph, and I'm going to draw some notation that I want you to get used to. First, my graph, I'm going to assume that this is a standard normal distribution. And then, because it's standard, my mu, right at the middle, at the high point, is 0. And so 1.58 would be somewhere over here. I want the probability that it's less than 1.58, so I'm going to want to figure out this area less than 1.58. So I must be shading the area to the left. So that's a graphical representation of what I'm looking for. Now, in terms of a formula, I want to find the probability that my random variable is less than 1.58. So this is what I'm looking for. Now, if I was using the table, I would look at the table where I see 1.5 in the column and then 0.08 on the top row, and then I would find out where it is. But we're going to use a calculator, so let's see how the calculator is going to work out here. Now, this is another distribution. A binomial PDF is a binomial distribution. This is a normal distribution, so it's another distribution. So you should probably guess that you're going to be also looking at the second function vars. So let's go to second function vars, which is a handful of distribution. And the first two are the normal PDF and normal CDF. Okay? Let me tell you now, in this class, you will never use normal PDF. You will never use normal PDF in this class. Okay? So whenever you're dealing with the normal distribution, it's always normal CDF. Okay, binomial, binom PDF, binom CDF, we'll use both for the binomial distribution. For the normal distribution, always CDF. So that goes in your notes somewhere. Frank probably has it in his notes as well. So in this case, we'll use a normal CDF. Now, the key for the normal CDF, it's going to ask for two things. Actually, it's going to ask for four things. Two or four. For the normal CDF, it's going to ask for a low. Let me write this down first. So for a normal CDF, it's going to ask for a low value, it's going to ask for a high value, and then it's going to ask for a mean and a standard deviation. It's going to ask for four things. Now, I don't know if I should even tell you this, but if your mean is 0 and your standard deviation is 1, you can just disregard these other two things and just put low and high and close the parentheses and be done with it. So if you only have two arguments for the normal CDF, it's going to assume that you're looking at the standard normal distribution and the mean is 0, standard deviation is 1. But I think I want you to get used to more practically, you're going to be using a normal distribution where the mean is not necessarily 0 and the standard deviation is not necessarily 1. So for us, let's get used to using a normal CDF with 4 arguments, and we'll always put in the mean and standard deviation. Okay, so let's stick with that idea. So normal CDF, low and high. Now, this is where the graph would come in handy. Just by drawing the graph, I can see that my high, my shaded region, right? So I'm looking for what's bounding my shaded region. I look at my high as 1.58. My low, what did I say about the normal distribution? What? It goes all the way to negative infinity. Now, there's no negative infinity button in my calculator. So the thing to do is you put in a negative and a really, really low number. I mean, by number, low number, negative number, I mean a really high number. So a high number would be 9,999, or maybe 99,990, or maybe 99 million. Uh-oh. Let's go with this one for now. 1, 2, 3, 4. So 99,999 negative. That's not infinity, but it sure is way out there, right? So that's my low. My high is going to be 1.58. And if I stop here, I'm good because it's automatically going to assume that your mean is 0 and standard deviation is 1. But remember, I want you to get used to just putting the mean and the standard deviation all the time. And what I found out here is that if I don't close the parentheses, everything is still going to be okay. but it's probably good practice to close the parentheses anyways. So 0.9429, usually we want to round this off to 4 decimal places because the table of values they give is rounded off to 4 decimal places. And this is where my whole idea about probability, this is a probability after all. I like to round off my probabilities to 4 decimal places. So if you're not sure, just write down all the numbers you see in your calculator and you'll be safe. All right. Now, before I write this down in my paper, I want to give you what I like to use for infinity. Okay, so I'm going to do the normal CDF again. And for infinity, remember that E business, scientific notation? It tells you the number of zeros to add on. So I'm going to say 1. I have a negative here because it's negative. But my infinity is going to be denoted by 1. Right above the comma, so that second function in the comma, is that E business. That's the scientific notation. And then I'm going to put 99. So this is 1 with 99 zeros. That's almost Google. You guys know what a Google is? Kids these days, my kids know what a Google is because they learn it from school. A Google is 1 with 100 zeros. That's a Google. You can Google it. It's not spelled Google like Google, but it's Googal or something like that. Some mathematician wanted to denote it, and then his daughter said Google, and so that's how the name stuck. I'm just saying. All right, so minus infinity, comma 1.58. And just to show you, if I don't put in the mean and standard deviation, it's going to assume it's 0 and 1. So I'm just going to close the parentheses and press equals or enter, and I should get the same answer. I do get the same answer, pretty much the same, consistent all the way through up to 9 or 10 decimal places, however many decimal places they have here. So, one e to the 99 will be our version of infinity. Okay, so whenever you're using normal CDF and then you're saying it's less than something or even greater than something, you're looking at greater than something being going off to positive infinity, we'll consider that 1 e to the 99. And then my notation here got messed up. Oh, my L fell. Okay, so any questions about the calculator? Yes?
So if it was like basically 1.58 was negative, and like we're trying to find the area to the right, you would just have the infinity just be positive?
Yes. So the low would be 1.58 or negative 1.58, and then the high would be positive infinity. Yep. And we'll see a couple examples like that too. Okay, so is this example clear? I think for me, at least for me, the graph is a really good indicator of trying to figure out what your low and your high values are. If you're able to shade it in the graph, then you can take a look at see where the low and the high is. All right, let's do another example. This one takes a look at the opposite side, the above business. So we'll look at it's the same scenario except, the last part over here. Find the probability that it reads between 1.23 or above negative 1.23 degrees. So again, I would draw my graph. My mean is 0 right here. My standard deviation is 1. I don't need to mark that anywhere in my graph. I do want to figure out where my low and high values are. So they say above negative 1.23. Negative 1.23 should be over here. And then I want above that. So I'm going to mark it from here, and I'm going to shade in everything above that. Now, one thing I didn't mention earlier, I forgot to mention, is that the whole area under the curve is equal to 1. I'm shading in from negative 1.23 to everything above. Should my value be less than 1/2 or bigger than 1/2? 1/2 is right here, right? And then we have a little bit more than 1/2, so this should be bigger than 1/2. So just as another thing to, just watch out for, you're kind of checking yourself while you're doing these problems. You should expect this to be a number that's bigger than 1/2. Okay? All right. So I draw my graph and I begin writing my notation. My probability that it's above. So x is above, so that's a bigger than sign, negative 1.23. And then in the test and in the quizzes, I usually tell you, if you're going to do this in the calculator, write down the calculator command. So this would be what I would want you to write. So you're going to say, I'm going to use my normal CDF. My low value, I'm looking at my graph, my low value is negative 1.23. My high value is negative infinity. Now, since you're doing this by hand, you can write negative infinity, or you can write what you're going to type in your calculator. Oh, sorry, it's positive. Thank you. Whoops. Whoa, what? There it goes. Okay, so 1e to the 99. So either the symbol infinity or 1e to the 99 because you're writing it by hand anyways. The mean and the standard deviation. And then go to your calculator and punch it in. So second function, vars, normal CDF, negative 1.23. I don't know why it's going there. 1.23, comma 1. Second function, comma, that's e to the 99, comma 0, comma 1. Close the parentheses. So 89.06. I have a feeling that this computer will be crashing soon. What was it? 8906. Okay. So, yeah, that's all there is to it. In the other problems, when we start looking into the next section, we're dealing with general probability distributions. All it means is that our mean is not going to be 0 and our standard deviation is not going to be 1, but we're kind of primed to do that already anyways. All right, let me just walk through some of the things here that they have in the sheet of notes, and I'll have this in my sheet as well, or in the handouts that I'll have this PowerPoint presentation. So using the table, they got the same answer that we got, 0.9429 for the first problem. And then this is, I kept these slides because I just like the interpretation of that. So one interpretation for this is to say that the probability that one chosen thermometer will measure freezing in less than 1.58 degrees is the answer that we got, the probability, 0.9429. So it is a probability. Well, you look it up in the table by looking for 1.58. So 1.5 and then 8, and then that's that number. But we have a more precise way of doing things with our calculator. My cursor keeps going to the bottom right corner there. So one way to interpret this is through probabilities. Another way to interpret this is that out of all those thermometers, 94.29% of all the thermometers will have a reading that's less than 1.58 degrees. So those are the two ways to do it. So I would suggest that you just take a quick look at the slides, the PowerPoint slides, or even just look at the book, because the book has that as examples. So the two examples that we did deal with strictly greater than or strictly less than, but there's some examples that you can come up with where your z-value is between a low and a high. So that's easier for us because we don't have to use 1 e to the infinity business or 1 e to the 99. All right, we're running out of time, so I'm going to fly through a couple more of these things. Sometimes you might be asked to find a score, a z-score, where they give you the probability. So let's take a look at this particular problem. And I have this already set up in my extra sheet here. So sometimes you might be given a scenario, you might not be given a picture, but you're given a scenario to say, what is the value that's going to separate the top 5% from the bottom 95%? So one way to phrase this question is find value separating the top 5%. So what we're going to use is we're going to use an inverse norm. So we're going to use a calculator. They have ways of doing this using the table, but that becomes a lot more inaccurate actually. So we're going to stick with a calculator. And what we're going to use for the calculator is to find this value. We have to know what your mean is and your standard deviation. And then we're going to use INV norm, inverse norm. And then it's going to ask for three things. The first thing is going to ask for the area to the left. And that should be an area that's less than 1. And then it's going to ask for the mean and the standard deviation. So when they say top 5%, the 5%, the 0.05 is actually the area on the right side, which means the area on the left side is 0.95, right? 95%. So our answer here is going to be inverse norm. Area on the left is 95%. Our mean is 0. Our mean is 0. And our standard deviation is 1. So if we punch that into our calculator, inverse norm can be found in the same place where we find normal CDF. It should come right after the normal CDF. So inverse norm, 0.95, comma 0, comma 1, mean and standard deviation. And if you press enter, you should get 1.64. So usually they want this in 2 decimal places. Sometimes they want it in 3 decimal places. So we'll use 3 decimal places. And this is 1.645. Say it again?
They can ask you this for regular normative range.
Yes.
So we just change the mean and the standard deviation.
Yes. So for regular distribution, for regular normal distribution, you just change 0 and 1 to whatever number it is, and then you'll get it. All right? So I thought I was going to finish this. I didn't finish it. So what I'll do is I'll record the rest of the PowerPoint presentation, and I'll add that as a third lecture so that you'll have something to look at. All right? So next time we see each other, you guys will come in for a test. Good luck studying, and if you have any questions, you can try to ask online, or maybe I'll put a discussion board up or something like that.